So in case of the in the group is G1, right? So of course there are 12 colorings, right? There are 12 colorings when we are using two colors for red, right? So there are four squares. Two of them are always going to be colored red, right? So it doesn't matter, the first red or second red. There is no difference. So therefore, we need to just look at the all possible colorings under So basically, we have 4 factorial possibilities, but two of them are the same by 2 factorial. So you have the multi-set. This is the first thing that we learned in our course. So therefore, we have 12 colorings, and all are inequivalent under the trivial group, right? Because the identity group. Right? I mean, we are we are not allowing any changes to be made. So once you fix the 12 different colorings, they are all going to be inequivalent. Right? They are all different. So then G2 is the group where we allow the vertical reflection, right? So under vertical reflection, we can see that there are 6 inequivalent colorings. So why is this? For example, under the vertical reflection, you have RRBY, right? And it is basically like if you put a reflection, and then you have RRYB also, right? So RRBY and RRYB belong to this particular one class. Then similarly, you will see that under vertical reflection, this one, for example, right, is equivalent to RR, here, and B and Y are interchanged, right? Similarly, in each of these, you will see, you can all find, one another coloring to which this is actually identical under the reflection, right? So under reflection, you take the reflection of this, whatever you get, they are both equivalent. So you get 6 inequivalent colorings because these two are equivalent, these two are equivalent, these two are equivalent, these two are equivalent, etc. Right? So under the action of G2, you have exactly 6 colorings. Now under G3, okay, so reflection on the main diagonal, you will see it is slightly different. This is why I said G2 and G3 may be isomorphic as abstract subgroups, but under as symmetric groups, as permutation groups, they are different. For example, the action of G3 here is slightly different, right? So you will see that if you look at these colorings, right? So each of these colorings, under the reflection on the main diagonal, right? You will see another coloring, right? So you will see that, for example, B here and R here. This is a different coloring, and they are in equivalent. Again, Y and R are swapped. R and Y are swapped here, right? And similarly, R and B are swapped here. Again, Y and B are swapped here. So they are all having 2 elements in the class. So you will see that. But on the other hand, this one, right, B, Y, R, R, under reflection, this does not give anything else, right? So it remains the same. So therefore, there is only one element in its class. Similarly, if you look at YB and RR again, right? So there is only one element in this class. So these are different, right? Under the reflection with respect to main diagonal. So therefore, instead of the 6 we had here, right? 6 inequivalent colorings, we have 7 inequivalent colorings here, right? 1, 2, 3, 4, 5, and 6, 7. So G2 and G3 are isomorphic as abstract groups, but as permutation groups have different structure. And if you think about it, you will see that the difference comes from the difference in the cycle structure. Cycle lengths of elements are different. For example, here 1, 2, 3, 4, right? 1, 2 is a cycle, 3, 4 is a cycle. There are 2 cycles of length 2. On the other hand, under the reflection on the diagonal, you have 2 1 cycles and 1 2 cycle. So, and this is precisely what makes them different, right? So they are the difference in their action is precisely because of the difference in the cycle structure. So we will see more about this when we go. In fact, we are going to make use of precisely this observation, and that is the essential part of our Olias theory. And then we have G4, and G4 is the dihedral group, right? Dihedral group. G4 is the group of rotations of X, right? So all possible rotations, and there are 3 classes with 4 elements. Okay, so size of each class equals the order of the group. So why is that? For example, what is the order of the group? It is 4, right? There are 4 rotations of this identity, and then the 3 other rotations. And why they are why they're precisely 4? Because you will see that under rotation, and no coloring has symmetry with respect to this rotation, right? So you take any coloring that we have, right? If after rotation, if it remains, so we have this 12 colorings that we started with, right? We did not draw them, but think of this. You can take an example and draw them. So take any of the 12 different colorings. Not any. Take all the 12 different colorings and see that if you apply rotation, they are always going to be inequivalent. So therefore, there are 3 rotated elements other than the identity. So therefore, every class has exactly 4 elements. All the permutations, the identity as well as the other 3 permutations, they will all give different colorings, and each of them are equivalent under rotations. So therefore, you will see that if you rotate this, you will get 3 more different colorings. If you rotate this, you will get another 3. If you rotate this, you will get another 3. So therefore, all the 12 colorings appear here. So G4 is the group. Now G5 is the dihedral group. So under the dihedral group, we have only 2 elements. Okay. So the first class has 8 elements and second class has 4 elements. So you will see they are different because under the reflection, these R and R, right? They will not change, and therefore you have less number of elements in this class, and you can verify that this has 8 elements, right? So if you do all possible rotations and reflections, you will see that this will lead to 8 different objects that we are going to. Now, another observation that we can make is that the size of a class is the index in G of the subgroup fixing some fixed coloring in that class. Okay. So think of this and try to see why. Okay. So size of class is the the subgroup fixing some fixed coloring in that class for for any action of a group. This is a property that you can observe. Then you have finally G6, which is the set of all permutations. There is only one class, because we are saying that no matter what permutation we take, we get we are saying that they are all equivalent, right? So therefore, by permutation, you can always get a coloring from one to other. If the number of colors, number of times each color appears is the same, right? So since we started with saying that, now we have exactly 2 red squares and 1 blue and 1 yellow square. The number of cells in which red appears is always 2, right? And number of times blue appears is always 1. Number of times yellow appears is always 1, right? So therefore, we see that we see that when you take permutations, right, permutation cannot change the number of times a color appears, right? We are just saying that okay, this cell is mapped to this cell, that cell goes to this cell, etc. But the colorings remains same, for example, right? So therefore the number of times each color appears is always different. So that is it. So we have these 6 groups, and each group acts on the set of the set X, and then this action will also give different colorings, and then under this action of the permutations, we can say that they are basically symmetries that we are looking at of the object, and these symmetries will tell you how many different colorings we can have under the how many different inequivalent colorings are there under this action of symmetries. Now, so I forgot to mention what is index of a subgroup. So index of a subgroup is the number of cosets, left cosets, or equivalently number of right cosets. So when I said that the size of a class is the index in G, what I said is that if you look at the subgroup of a group that we are looking at, so take a subgroup and then look at what is the number of cosets this subgroup has in G, right? So that is called the index. So now it should make more sense, and then see why this is precisely the number of elements that appears in that class. Okay? So this should give you a better. Uh, now, this is why I said that we should also look at cosets. Now, consider the same set that we are looking at, where we consider the group which is the dihedral group, right, of all rotations and reflections. Now, under this, let us talk about by denoting by t of I comma j comma k. There is a comma missing here, I think. The number of inequivalent colorings using the colors R, B, and Y of X, using the color red I times, right? Color blue J times, and color yellow K times. Okay. So we have the set X. You have the dihedral group acting on this, and we are looking at the number of inequivalent colorings under the action of the dihedral group, where the red color appears I times precisely, blue color appears J times precisely, and yellow color appears K times. Right? So earlier we are looking at 2 red, 1 blue, and 1 yellow. Now we can say that okay, instead of this, let us say that we have I times red, J times blue, and K times yellow. Now, of course, if you are having X has exactly 4 elements, we should be clear that I plus J plus K must be 4, right? Because we are coloring all the cells, and it can only change within this restriction. Then now we want to collect the the information basically that counts, right? T of I j k for different values into a generating function, right? So this is something that we are already familiar with. So let us write fg of r comma b comma y as this summation over all I plus j plus k is equal to 4, because we have only 4 elements, and we have to color them all. So therefore, 4 times, the colors altogether can appear exactly 4 times. So I plus j plus k is equal to 4. T of I j k, right, which is the coefficient of r raised to I, b raised to j, and y raised to k. So r, b, y can be considered as variables, right, of the generating function. So instead of one variable, now we have several variables, right? So 3 variables here. So, and if you look at the coefficient of r raised to I, b raised to j, and y raised to k, it should precisely tell you, right, how many colorings are there, right? Inequivalent colorings are there under the action of g, that is y of g. Like I appears, r appears I times, b appears j times, and y appears k times, right? And that exactly that number is what we are looking at here, right? Which is t of I comma j comma k. So that is what we have. So we are putting it into the form of a generating function. This is how we define generating functions anyway. So our generating function fg of rby is this one. Now what is value? Okay, so we can verify that it's actually equal to. Okay, so you work out the details. Okay, looking at each color appears this, and you see that how many are there, and then apply the dihedral group and see how many inequivalent colorings are there. Okay, so you will see that this is actually going to be equal to r raised to 4 plus b raised to 4 plus y raised to 4, right? Because there is only one coloring where all the cells are colored with the red, right? Red appears 4 times. Means that I have one coloring and that's it. I mean, whatever else you are going to do, it's going to be the same, right? If you are using only red color. So similarly, b raised to 4, y raised to 4 is very clear. Similarly, r raised to b, r raised to 3b, right? So all three colored red and then one is blue. Of course, you have different colorings, but then under the action of dihedral group, you will see that they are all the same because by rotation you can get this, right? Similarly, rb raised to 3, r raised to 3y, and ry raised to 3, b raised to 3y, by raised to 3, right? So if I'm using only two colors, one of them 3 times, then you have this. But on the other hand, if you are using colors 2 times, right? So r, for example, is appearing 2 times, r square, and b is appearing 2 times. Then you will see that you will see two different coloring, right? So even under the action of dihedral group, you will see that there are two different colorings are possible. And similarly for r square, y square, b square, y square, etc. And then, as we checked before, r square by, right? Right, r is appearing twice, b is appearing once, and y appearing once. This is precisely what we calculated in the previous example, right? Where we are looking at this, we say that there are two in this class, right? G5 has exactly two, right? These are the two representatives here. So you will get 2, and for all the other symmetric cases, right? rb square y, rby square. So check this. I mean, it's quite easy, and make sure that this is precisely the generating function that we are looking at. Now, it's easy to observe and also see why that fg of rby, right, is symmetric in all its variables, right? rb and y. Since the names of colors does not make any difference. I mean, I can call red as blue and blue as red, right? Just renaming. So therefore, it should be symmetric. Okay, so we have this, and now let us look at some things from this. So if you look at fg, right? Fg, and look at fg of r, b, and y. I substitute with the value 1, right? So r becomes 1, b becomes 1, and y becomes 1. And what happens to this right hand side, right? So you get 1 plus 1 plus 1 here, right? Then you have again 1 plus 1 plus 1 plus 1 plus 1 plus 1, right? 2 into 1 plus 1 plus 1, and 2 into 1 plus 1 plus 1, right? So altogether, what you will get? Okay. So see what you will get there, and you should get the total number of inequivalent coloring, right? I mean, without the without the restriction on a specific number of times each color appears, you will see that if you are using, the coloring using these colors on the four vertices, four squares, you will see that this is precisely the number of coloring possible, which is 3 plus 1, 2, 3, 4, 5, 6, right? 3 plus 6 plus 6 plus 6, right? Right. So 6 plus 6, 12 plus 1, 2, 3, 4, 5, 6 plus 6 plus another 3, right? So this will be your total number of inequivalent colors. So you can verify that. Now, to generalize, let us use an n element color set, right? Instead of the 3 element set, let us say that we are using R1, R2, R3, etc., Rn, right? To color the set X. So we use more colors, then what can we see? Right? So the names does not matter, only the multiplication of the colors matter, right? Like multiplicities of the colors. How many times a color appears can make the difference. And again, the order of this color, in which this, multiplicity occur also does not matter. So what are the possible cases? So one possible case is that all four colors are the same, right? We have R1 is appearing in all vertices, R2 is appearing all, etc. Or one color appears thrice and another one appears once, right? This is another possibility. We have only four colors to color, and four squares to color, right? Then two squares are given, the same color, and another two colors are given the same color, right? Using two different colors. Then one color appears twice, and two colors are appearing only once. Then four colors are all four distinct colors, right? So these are the possible cases, and there is nothing else one can easily verify. Now these 5 cases correspond to the 5 partitions of 4. This is something that you should observe, which may be not very easy, but if you think about this, it comes true. Okay, that is basically what are the partitions of 4? We have 4 by itself. Then you have 3 plus 1, right? 2 plus 2. These are the integer partitions where we have looked before. Then you have 2 plus 1 plus 1 and 1 plus 1 plus 1 plus 1, right? So this basically corresponds to partitions of integers, right? So if you have the total number of boxes to color is 4, then all it matters, right? If you have enough colors to color from, all it matters is that how many times a color appears, and basically the multiplicities of the colors. And since the order does not matter, you will get this as exactly the partitions of 4, not combinations, right? So with respect to the first one, you will see that all colors are same, A, they are all identical. Then for 3 plus 1, you have A and B, right? Then you have A, B, or A and A in the diagonal, B and B in the diagonal, right? They are different. Then you have A in the diagonal, B and C are different, right? So which is 2 plus 1 plus 1. And similarly, you have A here and B, C, again 2 plus 1 plus 1. Then you have all four different, so A, B, C, D, A, C, B, D, or A, C, D, B, right? So once you have this, it is easy to find out the generating function. So what is Fg of R1, R2, etc., Rn? It is summation over all I, Ri raised to 4. For different colors, you can have this all to be the same. Then if I and j are different, summation overall I not equal to j, r raised to ri raised to 3 and rj, right? For different I and j, right? We need use two colors. One appears 3 times, one appears only once. Then we use two colors, I and j are different, but I less than j, where because order does not matter, right? So ri appears twice and rj appears twice, right? But there are two possibilities here, right? One is One is I less than j, and then the other one I greater than j. Then again, one color RA appears twice, and RJ and RK appears exactly once. So I not equal to j, of course. I not equal to k also, and j is less than k. I know RJ and RK are different. But again, j is less than k and j is greater than k. Two different cases. So there are two into this. Similarly, you have 3 summation over I less than j less than k less than l, right? This inequality holds, and there are 3 such possible arrangements. And you will see that this is precisely the generating function that we have, right? And as we saw in the previous case, if you substitute for all the variables to be 1, it will give you the total number of inequivalent colorings, where I use exactly n colors. Okay, so you verify this, and you can find out the numbers if you want. And what is the number FG1111? That is precisely, so in the first case you have n, right? So n different colors we are using, and each one you will get 1. And then you have Ri cube Rj, right? I not equal to j. So there is n into n minus 1 cases, right? Good. First color I have n choices, second color I have n minus 1 choices. Similarly, for the third, I have 2 times n choose 2. Then you have 2 times n into n minus 1 choose 2, right? And for the finally, you have 3 times n choose 4. So you will see all these things, verify all these things. As a homework, you can think of this and try to verify these things. And what is this actually? I know this is the more interesting part. This FG1111 is actually equal to 1 by 8 n raised to 4 plus 2 n cube plus 3 n square plus 2 n. Okay. So if you simplify this, right, FG1111, you will see that you can write this as this formula. And 1 by 8 comes nicely. You can take 1 by 8 outside once you do this simplification. Okay. And then what we observe from here is that the denominator 8 is actually equal to the order of the dihedral group, right? So dihedral group G5 has exactly 8 elements, and 8 happens to be the denominator, and it's not a coincidence. We will see later. Now, the coefficient of n raised to I, right? N raised to 4, for example, right, is the number of permutations in G5 with I cycles. So how many permutations are there with 4 cycles? There is precisely 1, right? So therefore I get coefficient of n raised to 4 to be 1. Now similarly, you will have 2 permutations in G5, where where you have 3 cycles are let us look at the permutations actually, right? So what are the permutations in G5, right? So G5, has this identity. Then you have 1 2 4 3, right? 1 4 2 3 1 3 4 2, and then you have uh, 1 2 3 4 1 3 2 4 1 4 and 2 3 and 2 3 and 1 4, right? So these are the dihedral groups. And now what we are saying is that so how many like how many cycles are there with exactly how many pyramids are with exactly 3 cycles? So we want to count that, right? So we will see that, and this one, for where is that marker? Yeah, so I have this one has 3 cycles. This one has 3 cycles, right? Anything else has having 3 cycles? Nothing, right? So we have coefficient of this is going to be 2, right? Coefficient is 2 here. Similarly, you will see that permutation with exactly 2 cycles, so will be coefficient will be 3. There will be 3 of them, and 1 cycle there is 2 of them, right? And that is it. So this is an observation that we can make. Okay, and then yeah, so this is one example that I had already written here. Now we want to show that this is actually the case for all such situations, right? So you will have the coefficients of these terms are going to be precisely the number of uh, times uh, number of times you can find a permutation or number of permutations in the group that we are looking at, having exactly 3 cycles, exactly 4 cycles, exactly 2 cycles, and exactly 1 cycle, right? So this can be generalized. That is what it says. So here we have the Burnside's lemma. Burnside's lemma says the following. So let Y be a finite set, right? And G be a subgroup of Sy. Now, for some permutation in G, let's say pi, the set fix of pi is the set of all elements Y such that pi of Y is Y. That the elements which are unchanged under the action of pi, right? The permutations may not change some elements, right? So if I take for example the identity permutation does not change any element, right? Similarly, we have 1 going to itself, 2 going to itself, 3 and 4 are interchange, right, in the dihedral group that we looked at. That is another permutation where 1 and 2 are fixed, right? So similarly, given you know given a permutation, we can see the set of all elements that are fixed by this permutation. So that is the fix of pi. Now the cardinality of the set, right? So that is cardinality of x of pi is the number of cycles of length 1 in the permutation pi, right? That is clear because basically the cycle representation of the permutation tells you which are the elements that are mapped to itself. These are the unit cycles, right? When we put a single element in the bracket in the cycle notation, that tells you that these elements are the fixed elements, right? So the fix of pi is the number of cycles of length 1 in the permutation pi. Now, suppose we denote by Y mod G as the set of orbits of G. Okay, so what is the orbit of a group? Basically, when the group acts on a set, it basically moves the elements. So then we can look at the elements which come under a class, right? So we are saying about the classes. So some elements are basically moved to other elements, right? Mapped to other elements, and then this forms a subset. So this is basically the orbit. Then the cardinality of Y mod G is actually equal to 1 by cardinality of G. Summation over all the permutations in G, the cardinality of the fix of pi, right? Here is the number of orbits of G is equal to the average number of elements of Y fixed by the elements of G. This is what Burnside's lemma says. Okay, so we will see a proof for this in the next class.